Hello, good afternoon. So for today, I will be reporting the properties of tangent. So first, what is our objective? Our objective is to prove and apply theorems that relate tangents and radii. By the definition of properties of tangent, one tangent can touch a circle at only one point of the circle. A tangent never crosses a circle, which means cannot pass through the circle. A tangent never intersects the circle at 2 points. The tangent line is perpendicular to the radius of the circle. So to further understand the properties of tangent, we need to have an investigation. The concept tangent is important throughout mathematics. In one use, the term tangent names a line that is associated with circles. An investigation, thinking critically. In this figure, the line of sight from the tower looking to the horizon is described by ray Tx. Assuming that the Earth is sphere, x and m are point on a great circle. So as we can see here in the figure, we have ray Tx and we have here the circle. Number 1, give the intersection of the great circle and ray Tx. And number 2, explain why ray Tx cannot be called a secant. So we're about to explain why ray Tx cannot be called a secant. But before we start the investigation, we must further understand what is the concept of tangent. So as we see in the figure, we have here a circle and line. It is stated here that a tangent to a circle lies in the plane of the circle and intersects the circle in exactly 1 point. Remember this one? In exactly 1 point. That point is called the point of tangency. That point is called the point of tangency. In this figure, line TH is the tangent with point of tangency H. Thus, ray TH is a tangent ray and segment TH is a tangent segment. So remember that a tangent line intersects a circle at exactly 1 point, and a tangent line and the radius it intersects are perpendicular. That's why we have here the right angle. So to begin the investigation, we have here theorem 9.1. It states in that theorem that if a line is a tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So we can see here in the figure, we have here the radius, the tangent line creating a right angle, and point of tangency. Given L is tangent to circle O at point A. Prove that OA, segment OA, is perpendicular to L. So our plan is to use an indirect proof. Show that the negation of OA is perpendicular to line L leads to a contradiction. So here is our proof. Assume that segment OA is not perpendicular to line L. So basically, when we have here the negation, if the statement is segment OA is perpendicular to line L, then the negation of it is segment OA is not perpendicular to line L. Choose another point, point X, on line L such that segment OX is perpendicular to line L. Then OX is less than OA. So we have here the negation of the conclusion. Through a point not on a line, there is exactly one perpendicular to the line. The perpendicular segment from a point to a line is the shortest segment from the point to the line. So what is our contradiction? OA is less than OX. Since all points of tangents, since all points of tangent L are external to circle O except for A, which was given as being on the circle. So, by that contradiction, we can now conclude, or we have here the conclusion, since the assumption that segment OA is not perpendicular to L leads to a contradiction of the definition of tangent, it must be true that segment OA is perpendicular to L. And since it's already shown that the negation of segment OA perpendicular to L leads to a contradiction, it is now proven that segment OA is perpendicular to L. And in connection with the investigation, we have here the corollary 1 and the corollary 2. The corollary 1 states that two tangent segments from a common external point are congruent. We can see here in the figure, we have here circle Q and segment PS and segment RS. So according to corollary 1, we have here the common external point S and PS, segment PS and segment RS are congruent. Next one is we have the corollary 2. The two common rays from a common external point determine an angle that is bisected by the ray from the external point to the center of the circle. So looking at the figure, which of them are the two tangent rays? So the two tangent rays are ray SP and ray SR. And the common external point is point X, S. And we have here the ray SQ and ray SP and ray SR determine an angle that is bisected by a ray, which is the ray SQ, from the external point to the center of the circle. So from that, angle PSQ and angle RSQ are congruent by the corollary 2. Now next one we have theorem 9.2. In that theorem, it states that if a line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then the line is tangent to the circle. Now, to further understand and prove this theorem, we have here the given. Line L, we can see here in the figure, line L is perpendicular to segment OA at the point of tangency A. Now, we're going to prove that L is tangent to circle O. So to prove this, we have here the plan. So what's the plan? Use an indirect proof. Assume that line L is not tangent to circle O, but intersects circle O at another point, X. So example, segment PQ, please look in the figure, segment PQ and segment QR are tangent segments. Now, segment OP is equal to 3 and OQ is equals to 5. Find PQ and QR. Now, how are we going to find it? So by that given, a triangle is formed. Triangle OPQ is a right triangle by theorem 9.1. So remember that theorem 9.1, it states that if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. By the Pythagorean Theorem, PQ square, the square of PQ is equals to the square of 5 minus the square of 3, and PQ is equals to 4. Now, since PQ is equals to 4, by corollary 1 in theorem 9.1, it states that the point tangent segments from a point, two tangent segments from a common external point are congruent. Now, since they are congruent, QR is also equal to 4. Coplanar circles may have common tangent lines, and the circles themselves may also be tangent. Moving forward, a common tangent lines are internal tangents if they intersect the segment joining the centers of the two coplanar circles. So please look at the figure. Next one, common tangent lines are external tangents if they do not intersect the segment joining the centers of two coplanar circles. So we can now see here in the figure. Next one, tangent lines are internally tangent if one circle is in the interior of the other, except for the point where the circles are tangent to the line. So we can see here in the figure, we have two circles. The smaller circle is inside the bigger circle. Next one, tangent lines are externally tangent if all the points of one circle are exterior to those of the other, except the point where the circles are tangent to the same line. So the internally tangent, the circle, the other circle is inside the bigger circle. It is called internally tangent, while the externally tangent, the other circle is outside, and except the point where the circles are tangent to the same line. So letter A, it is externally tangent. Letter B, it is external tangent. Letter C, it is internally tangent. And last but not the least, the letter D, they are internal tangents. Now, moving forward, when a polygon is circumscribed about a circle, when we say circumscribe in terms of geometry, circumscribe means draw a figure around another, touching it at points but not cutting it. Each side is a tangent segment to the circle, and the circle is inscribed. When we say inscribed, it means to draw a figure or something within another so that their boundaries touch but do not intersect. Now, each side in a tangent segment to the circle, and the circle is inscribed in the polygon. By this example 2, circle O is inscribed in triangle ABC, and AD is equals to 30, BE is equals to 50, and CF is equals to 20. Now look at the figure. So A, what kind of triangle is triangle ADF? It is called isosceles triangle. Why? By the corollary 1, two tangent segments from a common external point are congruent. So segment AD is congruent to AF. And by the definition, isosceles triangle is a triangle that has two sides of equal length. Letter B, what kind of triangle is triangle ADO? Looking at the figure, since segment AB is tangent to circle O at point of tangency D, going back to theorem 9.1, if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So when we say, when it is perpendicular, it creates a right angle. Now, what kind of triangle is triangle ADO? It is a right triangle. Why? Right triangle is a right triangle in which one angle has right angle. So looking at the figure, basically, if the measure of angle EFC is 50, find the measure of angle C. So the answer is the measure of angle C is equals to 80. And if I'm not mistaken, if measure of angle EFC is 50, then FEC is also 50 degrees. Then measurement is 80 degrees. So the measure of angle M, or I mean the measure of angle C is 80 degrees. Try these class exercises. Classify each triangle, justify, then find the missing angle measures. Number 1, it is a right triangle, just like in the previous discussion. Theorem 9.1, if a line is tangent to a circle, then the line is perpendicular. So if it's perpendicular, it creates a right angle. Then it is a right triangle. So find the measure of angle B if the measure of angle A is 30. So 30 plus the measure of right angle, which is 90. So 90 plus 30 is equals to 120. So 180, which is the measure of a triangle, 180 minus 120 degrees is equals to 60. So the measure of angle B is equals to 60. Next one, it is an isosceles triangle because of the corollary 1. Two tangent segments from a common external points are congruent. So the external point is A. A ray AB is congruent to ray AC. So it is an isosceles triangle. It is an isosceles triangle if it has two sides of equal length. Angle ABC or angle B is equals to 65, then angle C is also 65 degrees also. Next one, we have here two right triangles. If the measure of angle BCD is equals to 120, find the measure of angle BCA. So the measure of angle BCA is equals to 60 because of the definition of angle bisector. Next, I have prepared 6 another examples for you to understand more about the properties of tangents. So let's begin at letter A. So we have here circle C and the external point B. BA is tangent to circle C and BD is tangent to circle C. So defining the corollary 1, two tangent segments from a common external points are congruent. So since they are congruent, BD is equals to 17 also. Next one, letter B. Segment AB is tangent to circle C. Find x to the nearest tenth. Segment BA is tangent to circle C, creating a right triangle. Using the Pythagorean Theorem by the definition for any right triangle with sides AB and hypotenuse C, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So our hypotenuse here is x plus 6. So where does 6 came from? You notice that AC is equals to 6. So that CB is equals to 6, which is the radius plus the x. Now, 6 raised to 2 plus 11 raised to 2 is equals to the square of the quantity of x plus 6. Simplifying, 36 plus 121 is equals to the square of the quantity x plus 6. Squaring both sides, we have the square of 157 is equals to x plus 6. And simplifying, subtracting both sides by 6, we have here x is approximately equals to 6.5. Next one, letter C, is segment AB tangent to circle OC. Now, how we are going to solve about it? So, if the statement says it is tangent, we can use the Pythagorean Theorem again. 20 square plus 75 square is we don't know if it's equals or not to 78 square. Now, if it's equal, then it is tangent, vice versa. Now, simplifying, we have 6025 is not equal to 6084. So, segment AB is not a tangent. Next one, letter D. Segment AD and segment BD are tangent to OC. Find the missing length, which is the x. Or I mean, just find x. Since by corollary 1, AB is congruent to DB, we can now have the equation 5x minus 11 is equals to 3x plus 5. 5x minus 3x is equals to 5 plus 11. Simplifying, we have 2x is equals to 16. Dividing both sides by 2, we have now x is equals to 8. So to check, 5 times 8 minus 11 is equals to 3 times 8 plus 5. Simplifying, we have 40 minus 11 and 24 plus 5. So 29 is equals to 29. Next one is segment AB is tangent to circle C. So using again the Pythagorean Theorem, 42 raised to 2 plus 56 raised to 2, and we are not yet sure if it's equals to 70 raised to 2. So simplifying, 42 raised to 2 plus 56 raised to 2 is equals to 4,900. And the square of 70 is equals to 4,900. And yes, AB is tangent. Last one, we have AB is tangent to OC. I mean, AB is tangent to circle C. Find x to the nearest tenth. Similarly to the previous example, we can use the Pythagorean Theorem. And our hypotenuse here is x plus 9 because the radius is 9. By that, we can now have the equation 9 squared plus 21 squared is equals to x plus 9 squared. Simplifying, 81 plus 441 is equals to x plus 9 squared. Squaring both sides and subtracting both sides by minus 9, the answer will be x is approximately equals to 13.8. And now we're done solving the examples regarding about the concepts of properties of tangents. Can you now prove and apply theorems that relate tangents and radii? I hope so. That's all for today's report. Keep safe and thank you for listening. This is John Decena. Thank you.